Our next our next guest also has some incredibly interesting information to share. Let's welcome Eyal Estrin to the meetup. Eyal is an information security and cloud architect with over 20 years of experience. He's the author of books, quote, Cloud Security Handbook, and another one, Security for Cloud Native Applications. And he's used that broad knowledge in infrastructure, in operating systems, and architecture. And Eyal has received all types of certifications, CISSP. Wow, there sure are a lot. Is this an alphabet soup of qualifications here? I mean, holy cow, he's approved by everyone. He's going to share his insights regarding security in the cloud native era. Welcome.
Thank you, Gary. Thank you so much, and thank you everyone for joining this short lecture about security in cloud native era. So you probably told most of the thing about me. So I'm a cloud security architect. I've been working in the cloud security industry since the end of 2015, so nearly a decade. I've authored 2 books, and I'm a blogger. I'm sharing a lot of knowledge on social media, mostly about cloud security and cloud adoption. I do believe that knowledge should be shared, and you can scan this QR code and you can contact me via any social media you can think of. So let's move on to the presentation itself. Before we begin, short disclaimer, this presentation and lecture present my personal views, not JP Morgan's or any other entity. I'm currently working in JP Morgan, so I'm obligated to put this disclaimer. So let's move on. This is the agenda for today. We're going to define some terminology. We're going to have a discussion about modern architecture, short discussion about containers and Kubernetes. Naturally, what we've heard so far was way deeper than what I'm going to talk about. Function as a service, CI/CD processes, infrastructure as code and policy as code, and lastly, we'll have some key takeaways. So before we begin, we're asking ourselves a single question: what is cloud native? What does it mean? So when I was looking at the web for official definition of cloud native, I found this definition in the CNCF website. Cloud native practices empower organizations to develop, build, and deploy workloads in computing environments, whether it's public, private, or hybrid cloud. It's characterized by loosely coupled systems that interoperate in a manner that is secure, resilient, manageable, sustainable, and observable. One of the most common ways for modern design architecture is to use APIs. There are various ways to use APIs. I'm guessing the most common one is RESTful API. APIs are suitable for communication between components when fast synchronous communication and small amounts of data are required. In this case, we can see a client talking to a server using a RESTful API. He sends some request, I don't know, provide me some information from the database, and the client receives a response from the server using a JSON format. If we are using RESTful APIs, here are some of the best practices. These are not all of the best practices, but at least some of them that I can think that are important enough. So the first thing is, whenever you're exposing an API, exposing using an API gateway. It allows you to enforce authentication and authorization mechanism, adds throttling, and basically this is the common way to expose APIs to customers. Secondly, the recommendation is to enforce traffic encryption. It keeps data confidentiality. There are a lot of data passed through the wire that is containing sensitive information, so we need to encrypt it in the transit. Third, we need to enforce identity and access management, meaning any request we're getting from a client, we need to authorize it and make sure that the client has the proper amount of permissions to do some actions, whether it's read information, update information, maybe even delete information. So we need to stick to the least privilege, the principle of least privilege. Next, since APIs are basically a piece of code, we need to make sure we're doing input and output validation, meaning we need to validate at the backend server, at our side, what type of character types are being shipped, whether it's integer or number or text or whatever it is, what is the minimum and maximum amount of characters, anything relates to the input that we're receiving. And output means making sure that something malicious that maybe we have stored at the backend database will not be exploited at the customer side, meaning we need to make sure no scripts are stored at the backend database. Next, if we're about to expose APIs to customers from the public internet, we need to make sure our APIs are protected, whether we're protecting them using a DDoS protection from a volumetric attacks, or whether we are putting some sort of an API gateway, an application, web application firewall, or anything that will allow us to at least mitigate application layer attacks. Lastly, auditing. We need to audit all the incoming requests, both for troubleshooting purpose and for incident response, because let's assume that we've been breached. We would like to see all the logs and see who was the attacker, what he was able to do with our system. So auditing, very important. The next modern design architecture is called event-driven architecture. It is suitable for asynchronous communication and when required to deliver large amounts of data. Common architecture can be pub-sub, when we have one component publishing a topic or a message and another component consuming it or subscribing to consuming information. Another way we have event triggering. And lastly, we have event streaming. In this specific diagram, we can see event triggering. We have a user who is uploading a file into an object storage. The action of file upload to the object storage triggers a function which do something with the files itself. For example, maybe takes the file, strip it from its metadata, like file date, file creation date, file size, file ownership, and maybe take this metadata and save it later on for database, for maybe we want to review what type of data do we have in terms of file inside an object storage. If we're using security, if we're using event-driven architecture, these are some of the security best practices. Since everything goes over the wire, we need to enforce traffic encryption between all components. We need to encrypt data at rest, and this specific use case, specifically for pub-sub queues, because even though one component publishes a topic and another component consumes it, for a certain amount of time, data is persistent at storage, so we need to make sure it's been encrypted and will not be accessible for unauthorized parties. Next, we need to enforce identity and access management, meaning we need to make sure, and again, this is very relevant for pub-sub queues, who has permission to push a message to a queue, and who has permission to read a message or maybe even delete a message afterward from a queue. Secret management, and we're going to talk about it more and more, you can see in the next slides. A very common way of communicating between, mostly for an app-to-app communication, maybe between services, maybe between microservices. So in case we need to transfer static credentials, whether it's API keys, passwords, or anything that is considered static, we should avoid storing it hard-coded as part of our code or configuration files or open object storage packets. We should always use secret management for managing the entire life cycle of the secret, from the secret generation, secret storage, retrieval, rotation, and maybe lastly, revocation when we no longer need it. And as I mentioned before, audit all requests. Again, we still need to audit any requests coming from the customers, both for troubleshooting and for incident response purpose. We talked in the presentation, it was mentioned containers and Kubernetes. So in a brief, containers are a common way to package and deploy cloud native applications. It has large industry and community support. Containers can be developed, packed, and deployed anywhere, from the developer's laptop till full production grade. And specifically, Kubernetes is considered the de facto standard for container orchestrators. And it currently is supported by all major hyperscale cloud providers. They offer managed Kubernetes service, meaning they're responsible for the control plane. We don't need really to manage about the Kubernetes engine itself, but we're in charge of deploying new application, maybe making changes to the scalability of the Kubernetes itself, maybe securing the boundaries of the Kubernetes itself. But it's a common way to consume Kubernetes using a managed service. Some high-level security best practices for security in containers. Since the work of containers is mostly around container images, when we're building container images, the first best practice is avoid using root privileges inside the containers. The reason for it is because if somebody was able to hack the specific running container, he will be able to take charge of it. Maybe he will be able to gain access to other resources within our ecosystem. So we need to avoid using root privileges. If we're building the container images by ourselves, which is highly recommended, we should always use the minimum number of binaries and libraries. Again, decrease the attack surface. We should scan container images for third-party vulnerabilities, not just for the components themselves, like binaries, libraries, but also for the component, the dependencies that the binaries may be dependent on. So it's very critical. We should do it in an automated way to limit the exposure on our container images. Since it's very common for container to run code that we develop, whether it's Java, Python, or whatever language we decide to use, we should use static code analysis to scan the code inside the container image, usually during the build process, to make sure we don't have any code vulnerabilities that we are packaging in our applications. Another common best practice is to sign the container image itself and to store it in a private container registry. This makes sure that we're controlling which images will be used to deploy our application in any of the stages up to production. And we can validate using a digital certificate that the image was signed by us, that it wasn't tampered by unknown party. Again, secret management, we're gonna hear it again and again. Containers using secrets as static credentials to get access to other resources, sometimes between containers, sometimes a container needs static credentials to get access to a backend database. We should never use static credentials or secrets inside our container images or code or configuration files. We should always connect the container itself to a secret manager to maintain the entire life cycle of the secrets. Some high-level security best practices for securing Kubernetes. When we're deploying the initial Kubernetes server, the initial Kubernetes cluster, we need to deploy it as a private cluster, meaning it won't be exposed to external parties, probably be located in a private subnet that only we can control. The reason for it, we want to protect the API server, the most critical component of the Kubernetes cluster, which controls both API calls from inbound from external customers, and API calls within the cluster itself. So it's highly critical component, we need to protect it. Another common best practice is to use confidential computing for the worker nodes. The worker nodes are the node itself of the cluster where we deploy our application or containers on top of the worker nodes. Confidential computing is a technology currently supported by all major cloud providers in different variations. It allows us another level of protection. If so far we talked about protection at transit and at rest, confidential computing actually looks at it while running the application in memory. For example, we have sensitive information running inside a container. Who can access the secrets or the encryption keys running inside the memory? So confidential computing makes sure that any access to the secret information, to the sensitive information, will be attested at the CPU level. So confidential computing currently supported by all hyperscale cloud providers. Another recommendation is to use container operating system for the worker nodes. Instead of using the standard Linux operating system as for the worker nodes to deploy containers, container operating system are specific type of operating system, usually Linux. It's a hardened operating system, contains bare minimum amount of binaries with only one role, to be able to run containers on top of it. So Amazon has its implementation, Google has its implementation, Red Hat has its own implementation. So as a best practice, try to use container operating system instead of the standard Linux OS. Another best practice is to separate applications with different namespaces so that we can do some sort of isolation on top of Kubernetes, making sure that each application can access resources only that is required. Meaning, if let's say we have a pod-to-pod communication for a specific application, it's okay for them to communicate, but we don't want to make sure that other applications running on the same cluster will be able to access resources from our specific application. So we need to differentiate using different namespaces. Role-based access control, as any other application, Kubernetes has a built-in mechanism for role-based access control. And the nice thing regarding working with a managed Kubernetes service from each of the hyperscale cloud providers is the fact that they have built-in integration with the role-based access control of the Kubernetes. Meaning, we can use, let's say, Microsoft Entra ID or AWS IAM and use the identities, whether it's a human identities for managing the cluster, or maybe it's an application identities for communicating between resources. We can combine it together and make sure that we're using the least privileges using the built-in Kubernetes role-based access control. If we're already talking about pod-to-pod communication, it's a very common practice to make sure that even multiple pods running on top of the same Kubernetes cluster, they may not have business reasons to communicate between each other. So instead of using a flat network where every pod can speak to every pod, we should limit the communication between the pods according to business needs using network policies, which are layer 4 access policies, but for within cluster communication. As with any other application we used to have in the past, we should enforce traffic encryption even between pods and from pods to other resources in the cloud ecosystem. For example, communication between a pod and a backend database, or a backend or an object storage, for example. In order to keep data confidentiality, we should encrypt traffic as well. And lastly, the etcd is the built-in configuration database of the Kubernetes. Since it contains sensitive information such as which application do we have currently in memory, how many pods do we need to deploy for each application, and there are more configuration resides inside the etcd. We should encrypt it at rest and control the encryption keys, naturally. And lastly, Kubernetes, as in any other container-based application, uses secrets or static credentials to communicate with other resources in the cloud ecosystem. We should always use secret managers to manage the entire life cycle of the secrets. Function as a service sometimes refers to as serverless, but function as a service is a cloud computing model that provides a platform for executing event-triggered functions, allowing for automatic scaling without manual intervention. What does it mean? Let's say we have a piece of code that we can wrap it inside sometimes inside a container. But anyway, we can upload it into a fully managed environment managed by the cloud provider for running specific actions. For example, I don't know, as I showed before, a user uploads a file into an object storage, which triggers a function that do some actions with the information, with the file metadata, for example. So a very common way of using microservice or modern applications. We can combine containers with functions as well as part of modern applications. But one thing we need to recall, functions or FAS is mostly vendor opinionated, meaning vendor locking. I'm not saying it's something bad, but it's something, it's a risk we need to maintain somehow. We need to manage it. There is no feasible way really to take a function from AWS and ship it as is to Azure or Google. Even theoretically, if we're all writing on the same program language in Java or Python, whatever is supported by the cloud provider, it's not really something feasible to export and input to another cloud provider. Too much fine tuning. So for the time being, if you're already working with a specific cloud provider, perhaps you should make the best of using it. Some security best practices for functions. You should choose deployment location. What does it mean? At least from Amazon perspective, you have two ways of deploying Lambda functions, either outside the customer VPC or within a customer VPC. What's the difference? Let's say we have a function that needs to consume resources from external third party. Maybe it's external third party API. In this case, we may want to decide to deploy the function outside the customer VPC in order to get access to external resources. On the other hand, if we have a function that all it does is consume resources from internal or private resources, from object storage, from managed database, from a streaming database, whatever you can think of, in this case, we may want to deploy the function inside the customer VPC, have it have private IP, and be able to access resources in our cloud ecosystem. Since most of the work of functions is done over the wire, we should enforce traffic encryption to make sure that we keep data confidentiality, authentication, authorization of the function. When we deploy a new function, regardless of the cloud provider, one of the first things we need to do is assign it roles or authorization to do some action. For example, a function that needs to pull a file from object storage and maybe push some information into a backend database. So we need to keep the principle of least privileges when we are defining which roles will be assigned to a function. Since functions are basically a piece of code, we should always store function inside our own private code repository. It will allow us to control who has access to the code, who will be able to make changes, maybe do some rollback, who can deploy the code itself. So, and by the way, in some organization, code is also considered like sensitive information. So we should maintain it in our own private code repository. Secrets, very common way also for functions to consume resources from the cloud ecosystem and sometimes even from the on-prem. We should always use secret management to maintain the entire life cycle of the secret. Sometimes it's just an API call, provide me the secret. Sometimes it's using environment variables, which is encrypted. There are ways to do it as well, but we should never embed secrets or static credentials inside our code. And lastly, auditing. We should audit all the function capabilities or whatever API calls it did, both for troubleshooting purpose. Again, it's a fully closed environment, so it's very hard or challenging to troubleshoot issues. What happened to the function? Why did it crashed? Why did I don't know? He tried to get access and get denied. So we need to audit everything, and both for incident response, so that theoretically, and somebody was able to hack a specific running function and manipulate it to do some actions, we want to be able to investigate it. So auditing will allow us to do it. CI/CD, modern applications are built using a CI/CD process. Some of the benefits of using CI/CD: frequent release time. It will allow us to, some organizations are able to deploy a new version of their application once every couple of weeks, and some mature organizations can actually deploy new version of their code several times a day. So frequent release time, it enables automated testing. We can embed various types of testing as part of the develop and deploy process. It allows us to automate build, test, and deployment. It has modular design, meaning theoretically, each development team can design its build process slightly different. Maybe, I don't know, one development team is using functions, and it takes a code of the function from a code repository, make some changes to the code, and deploy it to dev or test environment, or even to production. Some other team may be using container images. So maybe their pipeline will be slightly different, and maybe they will be building or packaging a container image and then going to the artifact and deploy to, let's say, production. So it has modular design, and it improves developer productivity, because at the end of the day, developer, at least in a mature organization, owns the entire process from the code that he developed through the test until eventually being pushed to production. Some security best practices for CI/CD pipelines: authentication and authorization. In here, we're talking about who can push new code or who can deploy from an artifact. Traffic encryption, it allows us to protect not just the data passing over the wire, but also to protect configuration itself. Because again, some of the configuration, like environment variable may be sensitive or contain sensitive information, so we need to encrypt traffic as well. We should always use private code repositories and artifact registries, making sure that we're the only one who has authorization to push new code or pull code or container or function from a registry and eventually deploy it to production. Secret management, very common way. There are many scenarios where during the deployment or during the build process, we need to pull some sensitive information. So we should always make sure that we're connecting the CI/CD pipeline into our secret manager for maintaining the secret life cycle. I mentioned be able to integrate various tests as part of the CI/CD pipeline. So we can embed static or dynamic security tools to make sure that once the code was pulled from the code repository, we're scanning it, making sure it doesn't contain any vulnerabilities before we are pushing it, at least to the artifact, way before we're pushing it into production. We should embed software composition analysis tools. We talked about combining third-party packages or libraries, or even sometimes code snippet. So we should embed automated tools to make sure that whatever packages we're using as part of our application is always using, or hopefully using, a non-vulnerable components. Another recommendation is to embed software build of material tools. This is, in the past couple of years, we see it even in a regulation, we see it in many organizations, at least mature organizations. It will allow us to scan the code, to scan our entire artifact, and to be able to document what type of packages are we using, what type of package version, where did we upload it from, which license it uses, so that eventually, if theoretically tomorrow morning we'll have the next log4j vulnerability, instead of scratching our heads and asking, okay, am I vulnerable? Am I using this specific component? We can just go to this repository of the source of bill of material, review it, and be able to understand, at least on the surface, understand which components are we using. Maybe this specific package is built, is inside our container image, and maybe it's not been executed at all, but at least we know it's there, so we will be able to begin investigating whether or not we can replace it with a non-vulnerable component. And lastly, we need to recall that the CI/CD doesn't end at the deployment to production. There's still operational and maintenance phase, meaning patch management, vulnerability scanning, maybe from time to time penetration testing, so that eventually for the entire life cycle of our application, we know it remains secure, or if we find something, we need to fix it or at least mitigate it so it won't impact our customers. Infrastructure as code. So this is a declarative way that enables us to deploy an entire environment. It allows us to minimize the changes between the different SDLC stages. For example, I can develop a code that says, deploy me an application containing containers and a backend database within a specific network environment. With minor changes, usually pushed using environment variables, we can use the same code to deploy to different environments, to the dev, to the test, and finally to production. Since it's a piece of code, it allows us to audit code changes and roll back to previous version of our code. And by the way, as long as we are also keeping it in our own private code repository, we can also audit who made the change, so we can ask him, okay, what was the last thing you made, or why did you make this specific change? So auditing is very important as well. Common infrastructure as code, we have the HashiCorp Terraform. Now in the past year, we have the OpenTofu, which is the open source fork of Terraform. And it allows, it's currently supported by multiple cloud providers. It doesn't mean it's multi-cloud, but it only means that this code has different providers that can speak to different clouds. Now we have policy as code. So policy as code basically complements infrastructure as code. It allows us a couple of interesting capabilities. First, it allows us guardrails, meaning we can define specific rules, for example, block resources with public access. As long as we have guardrails, a developer can continue to do his work as he intended to do so. But from a security perspective, we can define what are the things that he will not be able to do. So if a developer says, I need to deploy an object storage, and maybe from some reason he made a mistake, and maybe by default it was left publicly accessible for the entire internet, we can make sure using policy as code to block this capability. So when he push code to production or to whatever environment he can think of, in the guardrail phase, if there's contradiction between the infrastructure as code and the policy as code wins. And we can decide whether or not we are breaking the build or whether we're just alerting somebody to make sure he fixed the deviation. Another thing we can do with policy as code, which is not really security related, is cost. We can enforce the use of specific resources. For example, a developer would like to deploy a virtual machine. Instead of him having the ability to deploy any type of virtual machine, including a very expensive one with a lot of memory and maybe a GPUs that eventually will have to pay a lot of money for it, we can enforce using policy as code and saying, okay, you will be able to deploy only specific amount of resources, meaning X amount of CPU and memory from a specific instance size, and that's it. So again, the developer will be able to accomplish what he wants to, eventually to deploy a new compute instance. However, he will be limited by the amount of versatility you can choose from. So we can also save some money. And another thing that is very interesting about policy as code, it's not just limited for guardrails. It can also allow us to enforce authorization. So we can enforce various authorization mechanisms, such as Kubernetes role-based access control, or even authorization mechanism for application. For example, there's the Open Policy Agent, or CEDAR, which is currently mainly used by AWS ecosystem, where we can just take the authorization component when we're developing an application from the infrastructure side outside of the application into a central location, so that whenever a customer is trying to authenticate and gain access to an application that we just exposed to him, we can evaluate what type of roles the specific customer will need. And we can limit or allow, as much as the business requires it, to enforce authorization, again, outside the infrastructure, outside the regular constraint of the cloud provider, just for the application purpose. Some high-level security best practices, both for infrastructure and policy as code. Regarding code repositories, we should always use private code repositories for both of those. We should enforce authorization to code repositories, who can push new code, who can pull it for deployment later on. Authentication authorization, who can actually deploy new environment. So this is very critical. At the end of the day, everything is API based, and we want to make sure that a human will not usually be able to deploy new environment to production. In test, in dev, that's completely fine, but usually in production, usually we're using service accounts in some sort of a break glass mechanism. So we need to enforce authentication and authorization. Static code analysis, again, it's code. There are open source tools and also commercial tools that we can use to scan our infrastructure as code itself, making sure it's not vulnerable. Maybe, I don't know, making sure it doesn't break anything, doesn't allow open source resources. So static code analysis tools will be able to accomplish this, or at least mitigate most of the risk related to infrastructure and policy as code. And lastly, secret management. There are tools to scan our code to make sure we're not storing static credentials inside our code. We should always connect to a secret manager and manage the entire lifecycle of the secrets. Some key takeaways from my presentation. We should always remember security fundamentals, from identity and access management, cryptography, network protection, and naturally auditing. We should use at least I recommend to use the public cloud built-in capabilities from key management services, secret management, the built-in audit trail. It comes out of the box. It may have with a small price, but it comes out of the box. All the services inside the cloud provider ecosystem supports it from day one. It's fully documented, highly recommended. Wait.
Oh, sorry about that. That was me.
Okay.
If you want to go back, well, there we go.
Okay. And lastly, we should embed security controls as part of the SDLC process. The entire concept of shift left, so modern application and with all the capabilities of the CI/CD pipeline really have the ability to allow us to embed security controls as part of from the development through the test, eventually to full production scale. So this is the end of my presentation. Thank you for listening. You're more than welcome to scan this QR code and connect with me via social networks, and I'm open for questions.
Indeed. Well, that was absolutely terrific. One of the things that comes to mind right away from one of the questions is, what are the main differences between on-prem and traditional, versus in the cloud? And this could be a very, very long webinar just by itself. But how would you, in 30 seconds or so, answer that question?
Okay, so when we looked at the traditional security, we usually looked at communication between a virtual machine, let's say, or a server and a backend database or a storage. But when we're looking at modern application, things slightly change. Now we need to deep dive into lower bits. For example, API calls. Maybe you haven't dealt with APIs in the past. Communication, even between pods, which mostly you could say it's a private communication. It's not really exposed even to our own network. We need to look at it as well. Modern design architecture, things like how do I enforce security between things that usually I haven't dealt with in the past? Maybe event-driven architecture, maybe a component between a server talking to a Kafka server, for example. Maybe we have experience with it. Maybe it's something new that we need to adapt and learn how to protect and try to detect security vulnerabilities in these specific components.
That was a great, concise answer. So thank you very, very much. That was incredibly interesting.